case 2 now. We have a multiple root. Maybe it's a fourth order equation and you've got two distinct ones, but maybe r equals 3 is a double root, okay? Let's do the case of a double root first. Case of multiple roots, okay. So first, consider the case where R1 is a double root, or a root multiplicity 2 is a double root. Okay. What I mean by double root, in other words, you get to this point over here, you solve this polynomial, you have a bunch of roots, and it comes out that maybe a root R1, we'll call it, just label R1, occurs twice. So you get R1 twice, and all the rest of them are distinct. The problem is, you see, if you write e to the R1x, and you do e to R1x again, it's the same thing. You're losing an independent solution because of that. And what we have to do is recover, because of that double root, the missing independent solution. We certainly know that e to the R1x is a solution, right? But the question is, what's that other solution corresponding to the double root? Because we need n independent solutions. Okay. And this is nothing more than basically a little bit of algebra over here. It's the following, okay? Let's see. Okay. We can look at this result. We started off at the very beginning, let y equal e to the rx be a solution. And then we found out that L operating e to the rx was our polynomial, or auxiliary equation, e to the rx. From your high school algebra, if R1 is a double root, I can factor out r minus R1 squared from there, right? Okay? So, what happens now is that L operating on e to the rx, okay, because R1 is a double root, you can factor out r minus R1 squared, right? And what's going to be left? It'll be a polynomial degree n minus 2. Let's just call that P of r. I don't care what it is. At this point, e to the rx. Okay, where P of r equals polynomial of degree n minus 2 right? Because the whole thing is a polynomial degree n, right? So if I have an r minus r1 squared, really I'm left with a polynomial degree n minus 2, and P of r1 is non-zero, right? Not equal to 0. Because if P of r1 was equal to 0, we'd have a triple root. And I said it's only a double root. Okay. Now here's something that's an ingenious thing which I saw, when I learned this course. Okay? What we do now is going to differentiate both sides of this guy with respect to r. Why not? Okay? It's true, right? This is general, right? Because it's a polynomial. So we have, what's the partial respect to r of L operating on e to the rx? Now, why did I write partial respect to r? Because x is a variable, and now I'm thinking of r as a variable also. And therefore, I put partial respect to r to say that, making you believe that x is fixed and taking a partial respect to r. Okay. What happens over here? You have to use the product rule 3 times, right? This contains r, that contains r, that contains r. So from the first guy, I get 2 r minus r1, right? P of r e to the rx. Then I get another term, r minus r1 squared, p prime of r, whatever that thing is, take its respect to r, e to the rx, and then one more. This is the key now. Then when I differentiate the third time, I get r minus r1 squared, p of r. And let's be careful. What's the respect to r of e to the rx? It's x e to the rx. Okay, let's be careful. Okay? If I differentiate e to the rx respect to x, it will be r e to the rx. With respect to r, it's x e to the rx. So, what do I observe now? The partial respect to r of L operating on e to the rx equals 0 at r equals r1. You see that? Okay? Look at the right-hand side and plug in r equals r1. That clearly goes to 0. That goes to 0, and that goes to 0. Okay? So, it looks like d by the r of L operating on e to the rx is equal to 0. Now, I can interchange the order of differentiation over here. It's like doing your partial derivatives that you did in calculus, You did things like the second partial of x expected x expected y. Remember, the order differentiation doesn't matter. There's a little technical thing there that the partials have to be continuous. But as engineers, let's just forget about that technical detail. And actually, it is continuous here. And we know that the order differentiation is immaterial when you do a mixed derivative. So I'm going to basically, what do you have on d by dr? That's obviously with respect to r. What's L? All the L derivatives are with respect to x, right? Right? Just look at it. So I'm going to change that now and just say, but the partial with respect to r of L operating on e to the rx is exactly equivalent to L operating on the partial with respect to r of e to the rx, right? Here I differentiate first with respect to x and then r. I'm going to say let's do an L d by dr, and we know that that is what? That's L. What's the respect to r of that? X e to the rx. Okay? But what did we just say over here? We said basically that take the partial respect to r of L operating on e to the rx, which is basically equal to that. It vanishes when r equals r1. Therefore, right, L operating on x e to the r1x is equal to 0. And there's our missing solution. It's x e to the r1x. Okay? So if r1 was a double root, okay, corresponding to that double root, you'd have, of course, e to the r1x. That would be one independent solution. And the second one, you just multiply it by x. And that gives you a second independent solution. And then the rest of them, which aren't multiple, is the same story as in case 1. And then altogether, you'll have n linearly independent solutions. Okay? Now, I'm not going to do this on the board, but I think you can see what's going to happen. Suppose R1 was a triple root. Okay? Then this would change and we'd say what? On the right-hand side, we have r minus r1 cubed, p of r e to the rx, where p of r be polynomial degree n minus 3. Then we differentiate with respect to r, we'd find this again, and you differentiate with respect to r again. And you'd find that you'll get the two missing solutions, x e to the r1x and x squared e to the r1x, and so forth. So let's just state the result for a polynomial where you have a root of multiplicity k. I don't care what it is. It could be 5, it could be 10. Okay? Okay, so this is case 2. And then you can do some problems on that one too. Okay. So, if r equals r1 is a root, you know what I mean by root, right? It's this polynomial that you're getting over here, right? If r equals r1 is a root of multiplicity k, say greater than 1. So we know how to do basically when k is equal to 2, it's going to be e to the r1x and x e to the r1x. So if r1 is equal to multiplicity k, then the corresponding linearly independent solutions are the following: e to the r1x, x e to the r1x, x squared e to the r1x, if you had a cube, a triple root, and then it goes down to x to the k minus 1 e to the r1x. And that's the story for multiple roots, no matter what the multiplicity is. Okay? So like you said, if you had a triple root, you'd have e to the r1x, x e to the r1x, and x squared e to the r1x. What's important is that the multiplicity of the root has to correspond to the number of independent solutions that you're going to have, right? And of course, this is just for this root r1. Then you got your other roots. If they're distinct, you know what to do. E to the r2x, e to the r3x. And if one of those was a multiple, you know what to do also. Okay? So now we know what to do in the case of distinct roots, and case 2 when you have a root of multiplicity, whatever it may be. Like I said, this you will not find in the book because they just do it for a special case, kind of a double root, and they just stated what happens when you get a root of multiplicity k. But it's easy enough to do it this way, so I include it. Okay, have some examples here? Sure, I do. I got, again, 2 examples, so let's do that here. Okay, I'm saying example 1, but it's, in case of example 1 for the multiple root. I guess it's example number 3 if you label them consecutively, right? We did 2 before, this would be the 3rd example, but now it's going to be a double root case. Okay, let's see what we got here. Second derivative of y with respect to x minus 10 dy dx plus 25y equals 0. Read that again. So I got the second derivative with respect to x minus 10 dy dx plus 25y equals 0. Okay? Well, it's a linear differential equation, constant coefficients, second order. So I write down my characteristic equation. I get r squared minus 10r plus 25 is equal to 0. You can see what happens over here. That becomes r minus 520 squared is equal to 0, right? And now, again, it has to have 2 roots. In this case, the first root r1 equals the second root r2, which is equal to plus 5. Okay? Now, where do students make mistakes? I've seen before. Just give you, let's learn from their mistakes. What many people do is they forget, that it's a double root, and then they write down. Some people will write down c1 e to the 5x, and then problem done. What's wrong with that? It's a second order equation, right? We have to have 2 independent solutions. So that's, get half credit, right? If that's what you write, okay? Then what's even worse, some people will do, I don't know if it's worse, but equally bad, c2 e to the 5x. Again, what is that? That's e to the 5x, c1 plus c2. It's the same as just constant e to the 5x. So that's not correct, okay? We recognize that 5 is a double root, and therefore, yes, we get e to the 5x, and then to get that second independent solution, what we just proved over there, you get another solution, c2, x e to the 5x. Now, you have 2 independent solutions for a second order homogeneous equation. If you don't believe me, okay, plug in x e to the 5x, and you will see it does satisfy the equation as well as e to the 5x. Okay? So that's what you do with, in case of a multiple root. Okay. Then I got another one, again, with this multiple root business. Second example here. Third order equation. Third derivative of y with respect to x. It doesn't look like a 3, does it? Third derivative of y with respect to x minus 5 times the second derivative of y with respect to x plus 8 dy dx minus 4y equals 0. Okay, so we got the third derivative of y with respect to x minus 5 second derivative plus 8 dy dx minus 4y equals 0. Okay. Let's write this now, okay? We assume a solution ERX, right? Our characteristic equation is r cubed minus 5r squared plus 8r minus 4 is equal to 0. Okay? Okay, let's see, maybe r equals 1. Does r equal 1 work? So r equal to 1, you get 1 minus 5 plus 8 minus 4. Yes, that works. So r equals 1 is a root. Okay, on exam, I wouldn't, I'd give you something where it factored, or I'd tell you, r equals 1 is a root. I mean, there are methods of solving polynomial equations, but that's more in the numerical analysis course. So I'll just say, note, r equals 1 is a root. You just plug it in.
That's not the general solution we want, right? It's just a.
Well, it's 1. Yeah, we got to get all 3 roots.
Yeah.
Exactly. Yeah. R equals 1 is a root. That's just so that you can get the rest of the roots. R equal 1 is a root. How do I know that? Just plug it in. You see that solves. Okay, if R equals, now we go back to our high school long division. I want to get the, what's left there. So we're going to have R cubed minus 5R squared plus 8R minus 4. If I did things right, I should get a 0 remainder, right? So we put an R squared up there. R squared times R minus 1 is R cubed minus R squared. Subtract, we get a minus 4R squared, right? Because it's minus 5R squared negative and negative, right? Plus 8R. I guess minus 4R over here. That's a minus 4R squared. Plus 4R, right? Hope I did this right. And then subtracting, we get 4R minus 4 plus 4. Yes, 4R minus 4, no 0 remainder. Okay. So the characteristic polynomial basically becomes R minus 1 times this quadratic. And I believe that's just R minus 2 squared, right? If I expand it, I get R squared minus 4R plus 4 is equal to 0. I can take away this. This is just, okay? But just, if you don't have, if you have a root, that's how you get the remaining ones. Okay, so what happens here? We got, again, remember, it's a third order equation. I must list all three roots. So the first root, R1 is equal to 1, right? But I got a double root, right? R2 equals R3 equals plus 2. Okay. So corresponding to this, I get e to the x, right? Here I get e to the 2x, but it's a double root, so I need x e to the 2x, right? So the general solution, y, is some arbitrary constant, okay, corresponding to R1, you get e to the x, plus c sub 2, e to the 2x, and again, the third independent solution, which is missing because we have a double root, we know it's x e to the 2x. Okay? And again, a great thing about this is you can check all these, You can plug in e to the x, make sure it solves, plug in e to the 2x, and plug in x e to the 2x. And there will be solutions. Okay? And again, it follows that's why I went through so much, and I went so carefully through the general theory, because you know what to look for. You have a third order linear equation, there has to be 3 independent solutions. Okay, and remember this technique that we're applying